Hello everyone, welcome to the lab this week. Today we're going to talk about data manipulation, so importing your data into R, working with it, changing it around, and then eventually exporting it in a format that you can open up in other programs like Excel, for example. And I'm actually going to approach this lab a little differently than the last couple. Instead of just sort of riffing and creating code on the fly, I have this script pre-prepared, and I'm going to work through these commands, talk about what each of them is doing. I might actually generate some new ones in the process of doing this, but this is just to help me stay on track, make sure that I'm hitting all the high points and not leaving anything out. Okay, so we're going to start by learning how to import data into R from a file that you have saved on your computer. So in this case, and I'm going to upload this onto Canvas, I have this file called LSGO measures, or lesser snow goose measures.csv. So I'm going to just double click on that, open it up, and take a look. By default on my computer, because I'm running Windows and I have Microsoft Office, it opens up these CSV files in Excel. And I can see from here that I have a number of different columns. So one column here has the Canadian Wildlife Service band number. So each goose gets its own leg band. Each goose has a different age. So in this case, G for all of them just means that these are goslings, not adults. It turns out snow geese come in a number of different color phases. And so W is for white and B is for blue phase. There's females and males in this data set. And then we have measured their head length. This is going to be in millimeters. Their tarsus length, so that's basically their leg bone. And then we have the length of their 9th primary feather, and I can see there's one NA in there. We measure their mass in grams, and then what habitat did they come from, good or poor habitat. And so this is the data that maybe I want to read into R, maybe I want to do some manipulation to it. Eventually I'd like to analyze it. We won't do that this week. And I want to show you how to bring this into R and begin working with it. Okay, now the first thing I need to do is figure out where this file is on my computer, because I'm going to need to tell R where to look for this file. And so the way to do that, actually there's a few different ways you can do that. But first I'm just going to open up my browser here, and I'm going to go to this file. And I can see up here at the top that there's all of these tabs that it's nested within. So it's in my libraries folder, documents, aisles. There's this big long path name. I can figure out what that complete path name is by right-clicking on that file and going to properties. And I can see this location file here. So because I'm on a PC, I can just select all of that. And I'm going to hold down Control and press C to copy it. And then if I bring it into R here, I can paste it, and I can see that this is a massive path length here. So, C, users, coons, LT, documents, and this is basically all the files that is nested within on my computer. Okay, I'm going to comment this out right now, just for the time being. But again, this is where my file is located. It's within this Module 3 lab folder on my computer. But what I need to do next is set what's called my working directory. And this is going to be where R is looking for any files that it wants to pull in. So I want to actually set my working directory to this path right here. And then R is going to be basically pointing into this folder. And when I go to import my files, it's going to grab them from there. So I can actually see where my current working directory is using this get working directory command right here. So I'm going to run that, and it tells me that, okay, right now R is pointing into my documents folder. So if I go to my Windows Explorer here, I have this documents folder, and so it's looking in here right now for that file. And obviously my LSGO, what was that file called? LSGO measures file isn't located in this file. I would have to go into a number of different files to go find it. Number of different folders here. So I need to change my working directory to this path length, and I do that by taking this big long string right here. I put it inside of these quotation marks. So this is again just a character string in here, and this is the location of my file that I'm going to read in. Now, actually, before I read this in, I just need to make one more change here. So, and this is just unique to R, but these backslashes here need to be going in the other direction. And so I'm just going to change, I think this is correct. You need to change them to this way, which is kind of annoying. I can see down here that this slash is going the other way, so I just want to make sure these slashes are going the other way. And I'll put one at the end there. I think that usually makes the computer a little happier. Okay, so I'm going to go ahead and run this, and that changes my working directory now to the folder that I want it to be in. And I can see down here that my working directory has changed, and it's pointing now into my Module 3 data manipulation, IELTS Module 3, and my lab folder. Now I can actually check what files are in that folder just to make sure I'm looking in the right place and that R is directed to the right place using this list.files command. And I'm just going to leave those parentheses empty there. When I run this, it tells me that I have two files in there. The first is lab3 data manipulation.r, so that's the file I'm working from right now. Just save that. And then the other file that's in there is my CSV file. So that's good. R is looking in the right place. I could also set the working directory by just creating an object that actually stores this path right here. So I'm just going to put this in quotation marks. R's giving me some trouble here. Quotation marks. And put those on the end. I'm just going to call this lab3 path. When I run that and I look at lab3 path, okay, so it's this big long character object here, and then I could go set the working directory to that lab3 path, and when I run that, it does the exact same thing. Now there's actually a third way to set the working directory. This is the one I use most commonly, is this third way. And basically, wherever my script is that I'm currently working from, so I'm currently working from this lab3 data manipulation.r script, all I need to do is go in RStudio to session, set working directory to source file location. And that's automatically going to set the working directory to wherever my current script is located. So if my script and my data are in the same folder, then R will be pointing in the right place to be able to grab that file. So if I run this, it basically does the same thing that my other two commands were doing. But this is nice because then I don't have to go through that whole hassle of trying to figure out where exactly that file is located by like right-clicking on it and going to properties and selecting all of this and changing all the backslashes. As long as my script is in the right folder, the same one as my data file, then I can just go to session, set working directory to source file location, and that works just as well. Okay, now I want to read in that file, and so I'm going to use this read.csv command. And let's just actually take a quick look. I'm going to go $read.csv just to take a look at it. The help file. Okay, and it's telling me here that I need to specify the file. So this is going to be the file name. And then I specify whether the header exists in that file or not. So essentially, is this first row, does it have the column names in that first row or not? Some files will and some files won't. And so you need to go and look at your file and see, are my column names in that first row? And in this case, they are. And so by default, the header is set to true when I'm using this read.csv file command. Now, if I was reading in a text file, I would use this read.table command. And again, I just specify the file name. The confusing part is that by default, it assumes that there is no header in a text file, whereas it assumes by default there is a header in a CSV file. I don't really know why it does that, because I think that they're both equally likely to have a header in that first row. Almost all the time, you're going to have a header in that first row. So just set header equal to true. And then the last thing I need to do is just tell it how is R separating those different columns. So when I open the file in Excel, it automatically knows that these are different columns. But if I don't have Excel and I was to open this file, I'm going to right-click. I'm going to go Open With. And I'm going to open it with Notepad. This is what a typical CSV file actually looks like. I wish I could. Let's see if I can make this a little bigger. Okay, this is what a CSV file looks like. So it's all of this data that's just separated by commas. Okay, now text files will sometimes be separated by commas, the different columns, or sometimes it'll be separated by a tab, or sometimes it will just be separated by a space. And so that's why we need to specify what is separating the columns in this file. I'm going to close this. Okay, so in this case, I'm opening a CSV file, and so the separator there is those commas. And now I just need to put in my file name here. So the file that I'm trying to open and read into R is called lsgo-measures.csv. So I'm just going to write that in here, lsgo-measures.csv. And I'm going to read it in, and I'm going to save it as an object. So dat.csv. Okay, so it looks like it worked. Let's take a look at it. I'm just going to run this head command to take a look at the first 5 rows. And I see that, okay, the object called dat.csv looks like it's read everything in correctly. Let's just check out the dimensions here. Dat.csv. Okay, 29 rows and 9 columns. Let's take a look at the summary statistics. Okay. Okay, there's some interesting stuff going on here that we'll come back to in a minute. I can take a look at the structure, dat.csv, using this str command. Let's just take a look at that. Okay, so it's telling me that the first column is an integer, the age is a factor, color is a factor. And so you can see that R automatically tries to determine what type of data belongs in each column. And so just based on the way the data looks in the first column, it's saying, oh, that's an integer, and this is my CWS leg bands, my Canadian Wildlife Service leg bands. It's saying, okay, those look all like integers pretty much. It's saying in the age column, those look like factors. So it looks like I have, well, all I have is G's in that first column. In the next column for color, it's telling me that it's reading that in as a factor. There's 2 different levels to that factor. So there's a B level and a W level. Same with sex. It has 2 levels. One's for female and one is for male. And then it knows that the head height, because those are all numbers in that column, it's reading that in as a numeric column, and so on. Okay, now I could actually do all of this, specify the path, and I could read it all in one step if I really wanted to. So the way I would do that is I'm going to use read.csv here. And then all I'm going to do is specify the entire path length, including the file name, all in one step. Okay, so I'm just copying this right now, and I'm going to paste it down here. Okay, so I've got my entire path length all the way to the, all the way to the folder here. So this is where it's looking. And then at the same time, I end it with /lsgo measures.csv. And so this is the full path all the way to my, why does it keep doing that? All the way to my CSV file. I say the header's true, and it's separated by a comma again. Okay, and I can read it in just like that. So this should work. Take a look at it. Let's just take a look at the head, and this is going to be the exact same thing as my other one. So again, it's just read it in. So instead of specifying the working directory, I can actually skip that whole step if I want, as long as I include the entire full path length all the way to that file, plus the file name right at the end. Then it doesn't even matter what the current working directory is, because I've just told the computer exactly where to go for that file, regardless of the working directory. Okay, just two different ways to get to the same result. I usually like to make sure that I have my working directory specified, and then it just saves some keystrokes here where I can just say, okay, LSGO measures. Makes just the code look a little cleaner. Having this big long file name inside that read.csv command is just a little bit confusing sometimes. Okay, you can also read in data using this read.table command. It just reads things in just a little bit differently, so take a look at it. If you want in the help page, sometimes it's useful, especially if you're reading in .txt files. Usually you're going to want to use read.table. And then again, you can just check what working directory you're currently in using this getwd command here. All right, so now we have our data read in, and now it's time to start manipulating it. So this is going to be basically checking that all of the columns and variables have been read in correctly and they're in the right format. We can start changing those formats if we need to. We can start cleaning the data, removing NA values, getting our descriptive statistics, visualizing the data. Everything that we've been doing in the last couple weeks is now what we're going to start doing with the data that we've just read in. Okay, so I'm going to start here. This section, I'm just going to remove everything from the working directory using this rm list equals ls command. Okay, everything's gone from my environment now. But you'll notice, even when I use this command, it doesn't change my current working directory. So my working directory is still pointed in the same place. Let's check this out. Get working directory. I run it, and it's still in the exact same place. Okay, that's good. If I leave R or RStudio, so I'm going to save this document, I'm going to exit RStudio. Okay, and I'm going to open it back up. I can see now that my working directory is not where it was before. So by default, again, it just points here. So now that I've started RStudio up again, I'm just going to come down here to my data manipulations area. Okay, I'm going to need to change my working directory. So I'm just going to set my working directory to the source file location. And I'm ready to go. So let's read in the data. I'm going to call it DAT. Again, I can just look at it. Okay, this is what we did a little bit earlier. I can look at the first 5 rows using the head command. I can look at the last 5 rows using the tail command. So that's new this week. These are the bottom 5 rows. Summarize the data using the summary command, which we did a few minutes ago. I can get the dimensions using DAT. I can get the names of the columns using this names command. So let's take a look at that. Okay, and again, these are characters. I can check, is this a data frame or not, using this is.data.frame command. And it tells me, yes, that's true, it is. And finally, I can take a look at the structure of the data using that structure command, which we did earlier. Okay, now because this is a data frame, I can actually extract or look at specific columns using this $sign command right there. And again, as you now know from the lecture and from the Module 1 recap video that I released last week, you can't use this if your data is in a matrix format. So that's where like this is.dataframe command is useful. It tells you, yes, this is a data frame. Okay, then I can actually use this $sign command if I want. So let's take a look at the sex column. I can do the same thing for age if I want. Habitat. I don't know why that says mass in grams. This is habitat type. Okay, and so I can see here that some rows have a value of good in them, some rows have a value of poor in them. I can use this unique command here, unique, to extract just to basically whittle that data down to just only the unique values. So when I run this unique command, it tells me good and poor, and it basically removes all the redundancies and just leaves one of each. Okay, now if I had like, well, here's a good example. Let's go unique. I'm going to create a vector here. I'm going to have some 4s, some 5s, some 6s, some 1s, some 3s. If I use this unique command on this vector right here, tells me that there's a 4, a 5, a 6, 1, and a 3. It doesn't tell me how many there are, but it tells me that these are the unique values in that vector. So this unique command can be pretty useful for just seeing what the different values are within each of your columns. And I use this a lot, this unique command, to error check my data and make sure I haven't made any typos. Because if I use this unique dat $habitat and I end up with good, poor, and then maybe capital P, capital O, capital O, capital R, I would see that, okay, I actually have 3 different values represented in here. 2 of them, though, should really be the same thing. I could go back to my data and fix that in the raw data file. Hope that makes sense. Okay, let's move on then to talking about data types and taking a look at the way R is treating these different data types within my data frame. So let's start off by looking at dat habitat again. And this is actually not a character vector. This is a factor vector. Okay, so it's treating it as a factor with 2 levels, good and poor. Now the difference between characters and factors is actually pretty subtle and kind of hard to explain. But here I'm going to create a new column in my data frame called habitat underscore car for character. And then I'm going to change, so my dat.habitat is a factor. I'm going to create a character vector, a character column in there. So go ahead and create that. Let's take a look. Head of dat. So I can see here that my habitat column has goods and poors in it. My habitat underscore character column also has goods and poors. And superficially, they look very similar. And it turns out, actually, when you're doing statistics in R, it actually doesn't make a difference whether they're characters or factors. R, behind the scenes, will actually just convert characters to factors for you, and it pretty much does the same thing. But there are some instances that we'll probably get into later in the course where it matters whether you're dealing with characters or factors. And so it is important to pay attention to that. Right now it might seem a little confusing, but in general, you're usually going to want to change your data, things like eye color, habitat type. You're going to want to treat them as factors in general. And then things like notes to yourself or comments, those you'll want to treat usually as characters. Essentially, R is just assigning a numeric value behind the scenes to factors. So it's giving it numbers like 1, 2, and 3 to just specify different levels, whereas it's not doing that for characters. And so you can read a little bit more about that online, and I'll actually try to see if I can find a few good resources to read about those differences. But for the most part, you shouldn't have to worry about that right now. Okay, so we have a numeric vector in my mass column. I can just check that here by reading in mass. And let's just say, what is the structure of dat mass? Tells me that it's an integer, which essentially behaves the same way in R as just a numeric vector. You can perform mathematical operations on it. I could add, subtract, multiply, do whatever I need to. And I can also create a logical vector by using these logical commands here. So here what I'm doing is I'm asking, okay, let's just check out first this dat/head height column. Okay, so I can see that it's numeric here. And now I'm going to ask for which of those are greater than 92. So I can, just looking at it, I can see that some are greater than 92 and some are not. And so I'm going to assign that to the object logic height. When I run that command, let's take a look at it. Now I've created a logical vector, and so it tells me each of those elements. So the first element was not greater than 92. The next one in that vector was not greater than 92. The third one here, 92.9, true. That one was greater than 92, and so on. And again, this can be useful for subsetting my data, so I could do something like, let's see here, dat head height, okay. And now I'm going to index it, so I'm going to select elements just based on logic.height. So what this is going to do is just pull out only the ones that are true and leave the ones that are false behind. Okay. So if I was to just run my head underscore height column, I get all of them. My logic.height vector has some falses and some trues. And now what this command, the whole command together, is going to do is it's going to only pull out the ones that have trues associated with them. Run that, and now I only have values that are greater than 92. So that's why logical vectors can be really useful sometimes. As we saw before, in the lecture I pointed this out, you can find missing values using this is.na command. So let's run that, check that out. And now what this has done is it's actually checked every single element in my entire data frame to see if it's an NA value. And so it's returning logical values in each of those cells. So it's telling me that this cell, this element was not an NA, this one was not an NA. All the ones that had false were not NAs, but I can see down here there is at least one NA in my data set. Okay, I can actually find the total number of NAs using the sum function, and by default R treats trues as 1 and falses as 0. So if I use this, the sum of is.na of the whole data frame, it's going to sum up all of the trues in there and tell me how many NAs are there total. And so there's only one NA total in my entire data frame. If I go back and look at it, I'm going to click up here. It opens up this nice table that I can look at, and I can see here's this one NA, and there aren't any others that are obviously present in there. So that can be useful for just seeing where you're missing data. If I want to omit those NAs, I can use this na.omit function. So let's first just take a look at the dimensions of my data frame, 29 rows and 10 columns. And now when I run this na.omit, first let's see how many NAs are left in my entire data frame. I'm going to use this sum function. So there's 0 NAs left in there. That's good. It's removed it. But when I look at my dimensions, I can see that it's basically removed the entire row. So I went from having 29 rows and 10 columns to having 28 rows and 10 columns. So this na.omit function will remove the entire row if there's any NAs present in that entire row. Sometimes that's useful and sometimes that's not, because sometimes I might have an NA value like in a column that I don't even really care about. Maybe it's my comment column, and for some individuals I have some comments, for other ones I just didn't have any comments on them. But if I was to use this na.omit on my whole data frame, then it might remove all the rows that I didn't have any comments for, and I usually probably don't want to do that. So you sometimes do have to be careful about what you're doing. Okay, I can create a list just using this list function. As I mentioned in the lecture, lists are really these very generic vectors that can hold pretty much anything you want. So each element can be completely different. So in this list, the first element is going to be my data frame. The second element is just summary statistics for that data frame. The third element is going to be the column names of that data frame. Go ahead and create this list, just showing you a couple new functions here, ways of storing your data. So, and then I can reference the elements in that list. That you do reference them a little differently than other things. I just use 2 square brackets here. So to get the first element of my list, I would do it like this. That returns my data frame because that was the first element that I stuck in my list. To get the second element of my list, I would do that. That tells me the summary statistics. If I want the third element of my list, I just change that to a 3, and that tells me the column names because that was the third element that I stuck in my list. If I wanted, I could just add a single character right there. And so now I could ask for the fourth element in my list, and it's just the letter A. Okay, so lists can be really useful for just storing assorted information that don't all have to be of the same type. So here we're just using them to store some just general summary information about the data here, and we can call it later if we want. Okay, we'll keep going here, just a few more functions that are useful here. So again, I can ask if my habitat column is a factor using this is.factor function. Okay, and it returns a true value, a logical value here, so yes it is. And then, as I mentioned before, you can change it to a factor if it wasn't, say it was read in as a character, using this factor function. And so, and then I could evaluate the structure of my whole data frame using this structure command. Okay, again, just reviewing a lot of the stuff we've already gone through. Now I can sort data using this sort command, so I mentioned this in the lecture, and it's going to sort numeric data from smallest to largest. So if I look at my CWS leg bands, these are numbers, and if I want to sort them, it's going to order them from smallest to largest here, which looks like it may have actually already been that way. Let's do a better example here. Let's do ordered dot head height. And I'm going to sort my dat head height. Okay, so if I just look at that data, it's out of order. Okay. And then when I run this command, and then I ask for my ordered.head height, I can see that's sorted from smallest to largest here. You notice too, I didn't point this out, but you can actually have periods in your object name. So periods or underscores, both of them work. Okay, subsetting is another great way to manipulate your data. And here we're just going to select information from our data frame based on specific criteria. So in this example, what I want to do is only pick out the data on females. So let's just take a look here at my sex column. So dat $sex. And I can see that there's some females and some males in there. Let's just take a look at the head of my data frame here. Okay, so what I want to do is keep all the rows that have F's in the sex column and remove all the rows that have M's in the sex column. So the way I do that is use the subset function. I'm going to create a new data frame called females here, and then the first part of this function, I specify the data frame that I'm trying to take a subset from. So that would be my full data frame. And then here, I'm going to say wherever sex is equal to F, I'm going to keep those rows only. So that's what this second argument is in my function here. You'll notice here I need to put two equal signs. So when I use one equal sign, like here, I'm actually setting the value of this object. When I use two equal signs, that's asking, is this true or false? So, for example, if I was to do dat sex equals F, this is going to return a list of trues and falses for which that column is equal to F. So let's check that out. I get 4 trues in a row and 1 false, and that's because I have 4 females in a row and then 1 male. So here I'm going to run this subset function. I'll check out my data frame here. Let's just check out the head of that data frame. And now I can see that only females have been included in my data frame and the males have been removed altogether. And so if I ask for, okay, what's the sex column of my females data frame, it should all be F's now for female because the males have all been removed. It still tells me that because it's a factor, it knows that there should be a level for M, but in my data frame itself, there actually aren't any left in there. Let's just take a look at this females data frame here again, and I can see again that all the individuals here are female, and then it includes all the measurements for them. Okay, another example using the subset function. Let's only select individuals that weigh more than 1,000 grams. So mass is greater than 1,000. I'm going to call this fat goslings here. And I'm going to take a subset of my entire data frame again. And then I'm going to I actually don't even need to include this part right there. And I'm just going to say, okay, wherever the mass column is greater than 1,000, keep those rows. All the other ones get rid of. So let's run that. Let's take a look at fat goslings. Actually, let's just visualize it up here. And I can see here that in my mass column, I only have values greater than 1,000. All the rows that had mass values less than 1,000 have been stripped out. Okay, so we saw earlier that I can use this greater than function to ask which values are greater than whatever number I want. I can use this double equals sign to find out which values are equal to whatever value I want. There's a couple other logical operators I can use, and so I can use this exclamation point to find out which values are not equal to the one that I want. So let's check out this example right here. I'm going to create a new data set called males only, and one way that I could do that is by subsetting the data and asking for all the values for which sex is equal to M. So go first. Let's just check out the head of males only. Okay, and all I have left are males in that data set. I could do the exact same thing by asking for all the rows that are not equal to female. So I'm going to call this males only 2. I'm going to subset my data set, and then I want only the rows that sex is not equal to. So I use this exclamation point and then this equal sign. This tells R to grab the ones that are not equal to F. So let's try that. And let's take a look at the head, the first 5 rows of this new data set I just created. And again, all the females are gone. So males only and males only 2 should actually be the exact same. And I can actually check that if I want. I could go males only equals males only 2. I use this double equal sign, and that will check are all the cells in males only equal to all the cells in males only 2? And they should be. When I run that, I see that it's all true, everything's true, and that means that these 2 methods are exactly the same. I've created the same data set twice, but in this case, I use this not equals sign to do that. Okay, I can use this AND operator to include multiple conditions. So maybe I don't only want female. I don't only want males here. Maybe I want males that are greater than 1,000 grams. Let's try that. I'm going to delete this previous example and create a new one here. So let's only select males that are greater than 1,000 grams. So I'm going to call this males greater than 1,000. I'm going to subset my data frame, and then I'm going to use this AND symbol to have 2 conditions in here. So the first one is going to be sex is equal to male. And then now I use this AND sign, and I want mass to be greater than 1,000. Let's run that. And now let's just take a look at my males greater than 1,000 data frame. Just take the head. Okay, so the sex is male for all of them, and the mass is greater than 1,000 for all of them. So I can use this to have 2 conditions and make sure that my data frame meets both of those conditions. The last operator here is this OR operator, and so this is this straight up and down. On my computer, if I hold down Shift and then right underneath my backspace key in the top right of my keyboard, there's a backslash, but if I hold Shift and press backslash, it creates that straight up and down sign, and that tells R that I'm looking for an OR command. Okay, so this right here tells R that I want the sex to be male, and at the same time, simultaneously, I want mass to be 1,000. And if both of those conditions aren't met at the same time, then it will not include that row in my new data set when I'm using the subset command. This OR tells R that I want at least one of those 2 conditions to be met. Okay, so let's try that. Let's say that I either want the 9th primary to be longer than 160, or I want mass to be greater than 96. Okay, 160 or the tarsus length to be greater than 96. So let's try that. I'll call this weird goslings. Okay, so I'm going to subset my data. Now I said I want my 9 primary to be greater than 160, or I want my tarsus length to be greater than, I think I said 96. Okay, so one of those two conditions has to be met, or that row will be excluded from my new subset. Okay, so let's run that, weird goslings. I'm going to come up here and I'm just going to look at this data frame. So let's take a look at this first row here. My tarsus length is not greater than 96, but my 9th primary is greater than 160. So one of those two conditions was met. This gosling does have a 9th primary longer than 160. Now let's check out the second gosling. This gosling has a tarsus that's greater than 96, so it meets this condition, but it does not meet the 9th primary condition. Yet it's still included because one of those two conditions was met. So both the conditions don't need to be met at the same time. That's where that OR command right here, this straight up and down line, can be really useful for subsetting your data. Okay, so again, we have our double equal sign. We have our not equals to. We have our and. We have our OR. These are all logical operators, and these will return true or false depending on whether these conditions are met. Okay, now this lab has already gone on for quite a while, so I think I'm going to stop there today. I had wanted to talk about how to use these apply commands. We'll talk about that next week. And I also wanted to talk about writing your own custom functions to do specific tasks, but we'll save that for next week as well. So just to recap what we did today, we talked about first setting your working directory and then importing data into R. Okay, that's really important. Then we talked about just looking at some summary statistics and checking out the structure of your data. That's always important. Visualizing the data frame columns, which we've been doing for the last couple weeks. I showed you this unique function. I showed you how to generate a logical vector here by using these logical operators. So asking, is head height greater than 92? And it'll return trues and falses depending on whether each element is greater than or less than 92. We talked about locating missing data using this is.na function, and then finding how many of them there are using the sum. I showed you how to create a list using this list function, and lists can hold all sorts of different types of information. We learned how to sort data from smallest to largest using this sort command. And then the last thing we worked on was these subset functions. And again, these are really important for pulling out data based on specific criteria. So showed you how to choose rows based on one specific criterion. So sex is female or mass is greater than 1,000. We talked about using this not equals to operator. And then we talked about using this and operator as well as this or operator, which do two different things. So the and operator means that both conditions must be met at the same time. And this OR operator means that only one of those two conditions needs to be met. So we'll leave that for now, and we'll finally finish with just exporting your data. So the way to export your data is using this write.table or write.csv command. And so we have a bunch of different data sets here that we've created. Let's go ahead and export some of them, and it works just the exact same way as importing them. So I'm going to use this write.csv command. I first tell R what data I want to export. So I'm going to export my fat goslings data set here. And now I just need to tell R what I want to call that file. So I'm going to call it fatgoslings.csv. Now, where's it going to put this file? It's going to put it in my current working directory, which I set way up at the top of this script. So I run this command. It looks like nothing happened, but now if I go into my working directory on my computer, I can see that I've created this fat goslings.csv file. When I double click on it to open it, I can see that it has all of the columns that I wanted. It even has my row indices included in there. And because this was my fat goslings file, all the goslings are greater than 1,000 grams in here. Okay, I can do the same thing with write.table. So that can output data in different formats, and just check. You can read a little bit more about that. Write.table help file. But that's all there really is to it. You just specify the file you want to export, what you want to call it, the new file that you're going to create. And then if you want to actually not include these row indices here, you can specify row.names equals false. So let's close this. Okay, run this command. Now that I've specified the row names are false, I don't have that first column that has the row indices. It just starts off with my CWS leg band column. Okay, that's where we're going to leave it today. Thanks for watching. Good luck with the assignment this week. A lot of it is going to involve data subsetting, so pay close attention to that part of this lab, and definitely post any questions you have on the discussion board. Good luck, everyone.